GATE 2021 Metallurgy question number 19. Consider homogeneous nucleation of a spherical solid in liquid. For a given undercooling, if the surface energy of a nucleus increases by 20%, the corresponding increase in percent in the critical radius of the nucleus is, okay. So this question deals with the homogeneous nucleation, and the equation that governs the nucleation, I'm noting it down for you, where delta GF is the free energy change. It is nothing but, since our solid is spherical, so the volume of sphere is 4 by 3 pi r cube GS minus GL, where GS and GL are solid free energy per unit volume and GL is liquid free energy per unit volume, plus 4 pi r square, where 4 pi r square is the surface area of the sphere and gamma is the surface energy per unit area of the solid liquid interface. Okay. So if I have to show it to you, let us say this is a liquid and there is a spherical nucleus which is solidifying. It is having a radius r. And the temperature is less than melting point temperature, so the liquid is undercooled. Okay. The G versus T curve. The temperature at which the Gibbs free energy for solid and liquid will be equal is known as melting point temperature. Melting point temperature, the Gibbs free of solid and liquid are equal, so the system is stable. At temperature less than Tm, at temperature less than melting point, the free energy for solid is less than the free energy for liquid. Okay. So solid phase is stable, and at temperature above melting point temperature, the free energy, Gibbs free energy for liquid is less than the Gibbs free energy for solid, so liquid is stable in this region above. Right? Now what you will observe is the GS minus GL is a negative term, at temperature less than the melting point. Okay. While this term is always positive. Okay. So if I have to plot the delta G curve versus R, this will be your always positive 4 pi r square gamma, and this represent your volume 4 by 3 pi r cube GS minus GL. Okay. So this is the free energy change. So net free energy change can be shown like this. Where this is the maximum delta G max and the radius of nucleus at which we get maximum free energy change is known as critical radius of nucleation, Why it is critical? Because for radius less than r star, the delta GF tends to increase with increase in the size of the nucleus, which is not favorable. So solidification won't proceed, the nucleus won't grow. Likewise, for radius more than r star or radius more than the critical radius, you will see that delta GF tends to decrease with increase in the size of the nucleus. So nucleus will grow. Okay, so that is a favorable position. Okay, so in order to find the expression for critical radius of nucleation, we will simply follow the principle of maxima and minima. We know that from the definition of critical radius of nucleation, delta G is maximum at r equal to r star. Delta G is equal to delta G max at r equal to critical radius. Okay. So all we have to do is we have to partially differentiate the expression for delta G with respect to r. At r equal to r star, we will get this expression as 0. Okay. I won't go in detail about the differentiation aspect. I will straight away jump to the conclusion. The expression for r star will come out to be equal to 2 times delta G upon delta G. Okay, where delta G represents your free energy change between solid and liquid. This is a kind of a driving force. Larger the driving force, smaller will be the r star value. Smaller r star means a smaller nucleus can survive during solidification, so that will promote the solidification growth. On the other hand, the surface energy per unit area at solid liquid interface, okay, it is a kind of obstacle. It is a kind of obstacle to the nucleation. Okay, it is an obstacle to nucleation. Okay, a kind of a barrier. Okay. Larger the surface energy, more will be the critical radius. So smaller nucleus will have to grow to a larger size to survive the nucleation kinetics. Okay. So coming back to the question, we will use this expression. It is given that the 20% change is there. 20% change is there in the surface energy. So from this expression, I can say that R star is directly proportional to the free energy change, or delta R upon R initial into 100, okay, will be equal to delta gamma upon gamma initial into 100. Okay, so what does the question tells? For a given undercooling, if the surface energy of nucleus increased by 20%, okay, so if the surface energy of the nucleus increased by 20%, so let us increase the surface energy by 20%. So 1.2 will be the final surface energy minus initial. Initial is 1 upon 1 into 100. You will get 20. And this will be equal to delta R upon R initial into 100. That is your percentage change in critical radius of nucleation. That is your answer, 20%. So it is your 20%. Okay. So corresponding increase in critical radius of nucleus is 20%. To know more about the derivation of this nucleation growth, you can refer lecture 90, Introduction to Material Science and Engineering by Professor Rajesh Prasad, Department of Applied Mechanics, IIT Delhi.